Let's solve example 6 to find the equation of the xy plane. To visualize this, we'll draw out the xyz coordinate axes. Using the right-hand rule, here is the x-axis, here's the y-axis, there's the z-axis. We want to know what is the equation for the xy plane. The xy plane is just the plane where we're just in the xy axes. We can just kind of pretend that the z doesn't exist anymore. We're just in the xy plane. What's the defining feature of the xy plane? Well, x and y can be anything at all. There's no restriction. But z has to be 0. We can't move vertically up or down. So if we just use the equation z equals 0, that will describe exactly the xy plane. X and y can be anything. There's no restrictions. But z must be 0. That gives us the xy plane. Let's take a look in GeoGebra. When you go to GeoGebra, it actually shows you the xy plane by default. You can turn that off in the settings. And we just found that the equation for that xy plane is z equals 0. There it is. As long as z equals 0, x and y can be anything at all, and we get the equation of the xy plane. Take a look at example 7. We want to find the distance from this point, -3, 5, 1, to several different things. We want to find the distance to this point. We'll just simply use the distance formula. Then we'll find the distance to the xy plane, and then to a couple of axes. Let's see how to do this. To find the distance from this point to this point, we simply use the distance formula as we have been. We have the distance equals the square root. I'll do 3 minus -3, 7 minus 5, and 1 minus 1. So 3 minus -3 will be 6 squared. 7 minus 5, 2 squared, subtracting the y components. Subtracting the z components, we have 1 minus 1 squared, which is 0 squared. So we have the square root of 6 squared plus 2 squared. 6 squared is 36, 2 squared is 4. We have the square root of 40, and that's the answer. That's the distance between this point and this point. How do we solve part B? What's the distance from this point to the xy plane? Let's try to draw it out to visualize this a little bit better. Here are the x, y, z coordinate axes. Here's x, here's y, and here's z. We're considering the point -3, 5, 1, so let's plot that point. We move a distance of -3 in the x direction. So here's -3. We move a distance of 5 in the y direction. So there's a distance of 5. And then we move a distance up 1 in the z direction. So vertically we move up 1. And we arrive at our point right here. So there's our point, -3, 5, 1. What is the distance from this point to the xy plane? How do we find that? Well, the xy plane has the equation z equals 0. It's just this plane here where x and y can be anything, but z must be 0. What's the distance from this point to that plane? We just move straight down in the z direction until we arrive at the plane. And that z direction, that's just the z value of the point. That's a distance of 1. So the distance from this point to the xy plane is simply the value of the z component. That's 1. How do we find the distance from this point to the x-axis? Here's the x-axis, and here's our point. We could have a bunch of different distances, and what we really want is the shortest distance. So we could take really any point along the x-axis, and we could find the distance, but some distances will be greater than others. So for example, if I take a point way over here, that's going to be really far from the point, and if I take a point over here, that'll be closer. What is the closest point along the x-axis? Well, it's the one straight over. It's this right here. This is the point -3, 0, 0. So if I want the distance from this point to the x-axis, I'm really asking for the distance from the point -3, 0, 0 to the point that I'm interested in. So we can find that using the distance formula. Using the distance formula, distance equals the square root. Let's take -3 minus 3, so that'd be -3 plus 3. That's 0. So 0 squared, and then 5 minus 0, that'd be 5 squared. 1 minus 0, that's 1 squared. We'll write out the details here. -3 minus -3 squared plus 5 minus 0 squared plus 1 minus 0 squared. The x components here just cancel out, and I have 5 squared plus 1 squared. 5 squared is 25, 1 squared is 1. 25 plus 1, 26. The distance is the square root of 26. That's the distance from the point that I'm interested in to the x-axis. Let's solve part D. What's the distance to the y-axis? Once again, we could really choose any point along the y-axis, but we want the shortest possible distance. which will be exactly perpendicular here. So this point here is the closest to the point negative 3, 5, 1. X and z will be 0, and y is going to be the y component of 5. So I want the distance from this point to 0, 5, 0. That's this point right here, 0, 5, 0. Use the distance formula again. We have distance equals the square root of negative 3 minus 0 squared plus 5 minus 5 squared plus 1 minus 0 squared. Simplifying, negative 3 squared is 9. 5 minus 5 is 0, so that's 0. 1 squared is 1, so square root of 9 plus 1. Square root of 10, that is the distance from this point to the y-axis. Let's take a look at the next example. Example 8 is a fairly conceptual example. We want to look at these three expressions that are given and figure out for each one what is the region in three-dimensional space that that expression is describing. So first of all, look at y squared equals 4. What region in 3 dimensions does this describe? Well, we could solve for y here. If we solve for y, we could take the square root of both sides. So we'd get y equals square root of 4, but we have to do plus and minus because we are introducing the square root. Plus and minus the square root of 4 is plus and minus 2. If y equals either negative 2 or positive 2, then y squared will be 4. So y could be either plus or minus 2. What does that look like? Well, if y equals negative 2, then that would be over about here. X and z can be anything. So x and z could be anything at all. We get the plane here passing through the point y equals negative 2. If y equals positive 2, we have the same sort of thing, but on the positive side. We have y equals positive 2, x can be anything at all, z can be anything at all, and we get a plane here that passes through y equals 2, and then the x and z values can be anything. So we have two parallel planes, one passing through negative 2 for the y-axis, one passing through positive 2. How about part B? Can we describe what x equals y looks like in 3 dimensions? Notice that there's no restriction on z here, so we can think of z being any value at all. If x equals y, just think for a second what this would look like in 2 dimensions. Think of the graph y equals x. If we graph that in 2 dimensions, we have the x-axis, we have the y-axis. Y equals x is this line right here. Now imagine the xy plane in 3 dimensions. And we're going to draw that same line in the xy plane in 3 dimensions, and then we'll extend it infinitely upward and downward in the positive and negative z direction. So y equals x in 3 dimensions. We get the line, but then this extends upward and downward in the positive and negative z directions. So a plane that looks something like this. It's hard to visualize here. We'll visualize it in GeoGebra in a little bit, but something like that. It's a plane that satisfies x equals y. The value of z is any positive or negative number. How about the expression in part C? X squared plus z squared is less than or equal to 9. Let's think of ignoring y for a minute and just drawing this on the xz axis. Let's just think of the x and z axes here. We'll just think of the xy plane and we'll draw this expression in the xy plane. Well, what does this look like? X squared plus y squared less than or equal to 9. If we had equality here, we'd have the equation of a circle with a radius 3. The inequality just means that we have all the interior of the circle as well. So if we were to plot this just in the xz plane, we'd get a circle in the xz plane with a radius of 3, and then we'd want to fill in this circle because we have all the values less than or equal to the 3 squared. So we have the circle of radius 3 with everything filled in. Y can be anything. So imagine taking this circle and extruding it in the plus and minus y direction. Just stretch it out. And the shape that we get is a cylinder. It's a filled cylinder as well. So we just have a cylinder with radius 3 that stretches infinitely far in the y directions, and it satisfies x squared plus z squared less than or equal to 9. Let's confirm our answers by plotting these in GeoGebra. Let's start by looking at the equation y squared equals 4. There it is. Those are the two planes, just as we expected. One passes through y equals negative 2. One passes through y equals positive 2. In the x and z directions, these planes extend infinitely far. But they both pass through, well, one passes through y equals negative 2, the other through y equals positive 2. Let's look at the equation x equals y. There we have the plane, which looks pretty much how we tried to graph it in 2 dimensions. Notice that if we just look straight down vertically from the top of the z-axis. The red axis is the x, the green axis is the y, and that plane now just looks like the line y equals x. If we add in the third variable z, since z is not in this equation, the plane just goes infinitely far in the positive and negative z directions. Let's take a look at that last inequality that we had. We want x squared plus z squared less than or equal to 9. Notice that GeoGebra does not graph what we were expecting. We were expecting a cylinder that goes parallel to the y-axis, and we don't have that. We have this funny looking disk. The reason is that GeoGebra can't handle this inequality here. So we're just going to say x squared plus z squared equals 9, and then we see the cylinder that we were expecting. And we know that in the inequality, the cylinder should actually be filled. But since Desmos can't handle the inequality, we've got to be content with having x squared plus z squared equals 9, and then just imagining filling in the entire cylinder to obtain the inequality. Finally, let's solve example 9. This should be fairly quick. We want to write an inequality that describes the region between the yz plane and the vertical plane x equals 4. Let's first draw in our axes. Using the right-hand rule, we have the x-axis, the y-axis, and the z-axis. First, let's talk about what the YZ plane is. The YZ plane is actually flush with the screen or with the paper here. So just imagine this plane that's perfectly in line with the surface of the screen. That is the YZ plane. We can write the equation of the YZ plane. The equation is x equals 0. Y and z can be anything at all, and x equals 0. Then we have the vertical plane x equals 4, so move a distance of 4 along the x-axis. So there's x equals 4. And we have a vertical plane again when y and z can be anything at all. This is parallel to the plane x equals 0, which is the YZ plane. And we want the entire region in between these two planes. That will be a solid region, a three-dimensional infinite wall stretching in all directions between x equals 4 and x equals 0. And we can describe this with the simple inequality, x is less than 4 and greater than 0. Y and z can be anything as long as the x values are between 0 and 4. That inequality describes the region between the YZ plane and the vertical plane x equals 4.